I will explain you theorem 26.6 in this video. Here you can see the statement of this theorem. Let f from x to y, they are given you a function, okay, that is f, and they are saying this f is a bijective and continuous function. Okay, the statement itself, they are given you these three things about this f, and then also they are talking about this x and this y also. They are saying this x is compact and this y is Hausdorff space. So if these conditions are there, then what you have to prove is then this f is homeomorphism. That is what we have to prove. Okay. So in the proof, what you will do is you just write what is given in the statement first. So first you have to write given f from x to y is a bijective continuous function. Write that. Okay. Here you can't see that, but you have to write. Okay. Then only it looks beautiful. The proof will look so good. Given f from x to y is a bijective continuous function. Also given what? X is compact and y is Hausdorff. These are the sentences you have to write from the statement of the theorem. And then what you have to prove? To prove f is homeomorphism. You are writing three sentences just by copying it down from the question, right? Okay. Now, what you are going to prove? To prove f is homeomorphism, you have to know something that before proving that, you have to know to say this f is homeomorphism. By the definition of homeomorphism, it is enough to prove f and f inverse are continuous. If you proved it, then automatically f is homeomorphism condition will be proved. To prove, once again I repeat, to prove f is homeomorphism, it is enough to prove f and f inverse are continuous. How I am saying that? I am saying this by the definition of homeomorphism. Is that clear? Okay. Now in this proof, you will prove only f inverse is continuous. You don't prove f is continuous. Why? Can you tell me why you don't need to prove f is continuous? The reason is because in the statement itself they are given you f is bijective and continuous function. The statement itself they have said f is continuous. So you have no need to say f is continuous again. Okay, so that is why here you have to prove f inverse is continuous only, because already you are having f is continuous. So we are going to prove f inverse is continuous now. Okay. So before proving that, you have to know something in general. I will explain you that. Okay. So if there is a function f from x to y means, to say this f is continuous, okay, to say f is continuous, what you will do is you will take a closed set from this y. That is, if you are taking a closed set A from this y, this is a closed set. That is, I will say A is closed in y. Okay. So if I take a closed set from y, the inverse of this closed set A will be closed in x. Okay, I will tell you. So I am writing this f inverse. Okay, inverse I am putting. F is this. The element present here is f. Inverse is I am putting. And what? The elements present, the closed set present in y is what? F inverse of A. A. Okay. The closed set present in y is what? A. So I am writing that y. This will be closed in x. Is that clear? So why I am saying this is, if you want to say f is continuous, it is enough to prove for every closed set A in y, for every closed set A in y, f inverse of A is closed in x. Okay, for every closed set A in y, there is a closed set f inverse of A in x. It is enough to prove that. If you prove f inverse of A is closed in x, then f is continuous condition will be automatically proved. Can you understand? So the same thing here, what you have to prove? F inverse is continuous is what we have to prove now, right? So f inverse means the mapping will be converted like this. F inverse from y to x. inverse mapping, no, inverse. So F inverse, no, so the mapping will be converted like this, y to x. So now you are taking a closed set from the same procedure that you have done to this. You are doing that same to here, okay. The reason why I explained this is I want you to compare these two, then only you can understand. So the same procedure I am doing here. I am taking a closed set from this here, okay, A, and inverse of this closed set will be closed. This is closed, okay, in x, okay. The inverse of this closed set is closed in y. That is, inverse of this closed set is what? What you have to do? First you have to write f. This what you have here, you have to write it. Here what you have? F inverse, right? And I will put inverse, okay. That is its inverse image. That is what the meaning. So first you have to write this, and then you put this inverse, and then what you write? Of A, right? A is this set. Similarly you write this, okay. Is closed in where? Closed in y. So that is what you are going to prove now. Here, to say F inverse is continuous, here what you are going to prove is, you are going to prove F inverse, the whole inverse of A is closed in y for every closed set A in X. Can you understand? This is what the sentence you are going to write in to prove condition, in to prove, okay. So this is what you are writing. This is what the logic behind it. So also you have to know something. F inverse, the whole inverse means what? This is equal to F, okay. F inverse, the whole inverse means what? F, right? When you find what is F inverse? F inverse can be written like 1 by F, the whole, this inverse. So 1 by F, the whole inverse can be written like F, right? Okay. This you will study in our very small classes. So F inverse, the whole inverse is F, right? You will use that in the proof. So that is why in advance I told you everything. Can you understand? This is the condition you have to prove to say F is continuous. This is the condition to say F inverse is continuous. Here you are not, we don't want to find to prove F is continuous, because already in the statement they are given you F is continuous. You are just in need to prove F inverse is continuous, okay. Okay, let's proceed the proof. So to prove F inverse is continuous, that is to prove F inverse, the whole inverse of A is closed in Y for every closed set A in X. To write this sentence, I explained these things, okay. Just before I explained all these things, just to keep you feel easy to write this sentence. Can you understand? If you are not able to understand it, go and what is that? Rewind the video and you can listen it again, okay. Okay, now here what you are doing is you are taking a closed set from X, okay. That is what you are. Let A be the closed set in X. If A is a closed set in X means you know that this is the closed subset of X. From X you are taking this A. It means what? This is a closed set you are saying. Is a set. Okay. What set? This is a closed set. So from X you are taking this A, right? So this A is what? This is the closed subset of this X, right? So that is what you are writing. Let A be the closed set in X means this A is what? Closed subset of this X. By a theorem we have every closed subset of X is compact space already you have in the statement. So using that you can say you have a theorem, every closed subspace or subset both gives you the same meaning. Every closed subspace of compact space is compact. Okay. Every closed subspace of lot of noise disturbances are here. Please tolerate. Okay. By a theorem, every closed subspace of compact space is compact. So here is a closed subset of a compact space X. Therefore, this closed subset A is compact you will get, right? So that is what by this theorem you can say A is compact. Since f is continuous, we are using this condition here to proceed this proof further. Since you are having f is continuous in the statement, right? So you are writing, since f is continuous, you are having this theorem. The image of a compact space. What is the image of compact space? If you have f is continuous means you are having a mapping like this, right? F from x to y is our mapping. Here image of a compact space means f of a, okay? This is a. The image of this a is f of a. Okay, this is the image of this set A. So image of this compact, here x is compact space, y is Hausdorff space. Already you know that. In the statement you are having. So image of the compact space here is f of a. Here you have f of a. Also under continuous map is compact. They are saying image of the compact space under continuous map is compact. That is what the definition. So here you are, what they are asking us to say from this statement is, here you are having f of a. This is the image of the compact space under the continuous function. So you can say this f of a is compact. This is compact, okay. In where it is compact, that is y. Okay. F of a is compact in y. That is what you are writing. You know that y is Hausdorff space. So you are writing, therefore f of a is a compact subset of a Hausdorff space y. This is what you are writing. Now again you are using a theorem. Every compact subset of a Hausdorff space is closed. Okay, that is what you are getting. So f of a is, here you have this f of a is the compact subspace of Hausdorff space, right? This is f of a. So you can say this f of a is closed by this theorem. So you are saying f of a is closed in where? Y. This Hausdorff space y. So hence you can say f is continuous, because in this line you have said that f inverse, the whole inverse of a is closed in y for every closed set a in x. You took this condition. By taking this you have to prove this. You proved this here also. F inverse, the whole inverse means, already I told you, f of a. So f of a is closed in y. You got it, right? In this line you have got it. F of a is closed in y. So you have proved the condition to say f inverse is continuous. So you can say f is homeomorphism. Hence the proof.